Hello everyone, welcome to MyWave. Today we're going to introduce one of our advanced RF products, the MyWave 958 Series Wideband Frequency Synthesizer. In this video, we will explain what a frequency synthesizer is, how it works, its key features, and its operating modes. A frequency synthesizer is a precision electronic device that generates a stable RF signal at a desired frequency. Unlike a simple oscillator, which produces only a fixed frequency, a synthesizer allows engineers to digitally control output frequency, frequency steps, frequency sweeping, frequency hopping, and reference synchronization. For example, an engineer may need a signal at 5 GHz, 10 GHz, 28 GHz, 60 GHz, or 90 GHz. A wideband synthesizer can generate these frequencies with high accuracy and stability. The core technology behind a synthesizer includes phase locked loop, stable reference oscillators, frequency multiplication, frequency division, and advanced microwave circuits. The PLL continuously compares the generated signal with the reference frequency and corrects any error, maintaining frequency accuracy and low phase noise. MyWave synthesizer is a GUI-controlled, frequency-agile wideband synthesizer designated for demanding RF and microwave applications. Depending on configuration, the 958 series provides ultra-wideband frequency coverage from 1 GHz to 110 GHz. The synthesizer combines wide frequency coverage, low phase noise performance, high frequency stability, programmable operation, and compact design in a single RF source. Modern RF systems require much more than a simple oscillator. Engineers need accurate frequency generation, low phase noise, frequency agility, repeatable measurements, and remote programmability. The MyWave 958 series provides these capabilities. In radar applications, radar systems often require rapid frequency changes for target detection, signal analysis, and frequency agility testing. The frequency hop capability allows engineers to create agile RF signals for radar development. In satellite communication applications, modern satellite systems operate in frequency bands such as X-band, Ku-band, Ka-band, Q-band, and V-band. A stable synthesizer is required for RF payload testing, up-converter and down-converter testing, local oscillator generation, and ground station verification. In electronic warfare applications, engineers need flexible RF sources for signal simulation, interference testing, and frequency agile systems. The wideband tuning range and hopping capability of the 958 series make it suitable for these environments. Let's look at the major features. The MyWave 958 series supports 5 operating modes. In CW or continuous wave mode, it generates a constant RF frequency for a stable signal measurements. In frequency sweep mode, it automatically sweeps across a programmed frequency range. In frequency hop mode, it rapidly switches between programmed frequency for agile RF operation. In external trigger mode, it allows the synthesizer to synchronize its frequency changes with an external control signal. An external trigger input can be used to precisely control events such as frequency hopping sequences, FSK modulation patterns, automated RF test sequences, radar timing synchronization, and communication system testing. The external trigger provides accurate timing control, allowing the synthesizer to change frequencies at a specific moment defined by external equipment. PWM or pulse width modulation mode is used when you need to generate a pulsed RF signal instead of a continuous RF carrier. In the MyWave synthesizer, PWM mode allows the RF output to be switched on and off at a controlled timing while keeping the PLL locked to the desired frequency. The 958 series supports wide range of external reference inputs from 10 GHz to 500 MHz. An external reference allows synchronization with high-frequency lab clocks or system references. This improves frequency accuracy, long-term stability, and multi-instrument synchronization. The synthesizer also supports an internal reference option. One of the important features of the synthesizer is its easy control interface. The system provides graphic user interface, Ether connectivity, Wi-Fi connectivity, and remote RF on and off control. Through the GUI, engineers can set output frequency, select operating mode, configure output parameters, control frequency hopping, and monitor system operation. Additional performance features are fine frequency adjustments with 0.01 resolution. Output power of 20 dBm or higher is available. Rapid frequency transitions in less than 10 microseconds. Low phase noise for high quality signal generation. Integrated digital step attenuator option up to 70 dB attenuation range. Switchable internal and external reference sources. A built-in temperature sensor for monitoring operating conditions. Programmable frequency control and flexible RF signal generation. One more feature is integrated phase shifter. MyWave 958 series can include an integrated phase shifter option for precise control of the RF output phase. The phase shifter allows engineers to adjust the signal phase electronically without changing the output frequency. Now let us look at how to operate the synthesizer. We will begin with mechanical connections. First, connect the wire labeled ground from the synthesizer to the negative or ground terminal of the 15 volts power supply. Next, connect the wire labeled plus 15 volts from the synthesizer to the positive output terminal of the 15 volts power supply. The 15 volts power supply provides power to the synthesizer unit. Please refer to the synthesizer datasheet for exact current requirement. If current requirement is 2 amps, then the power supply must have a minimum current capability of 2 amps. Once all connections are verified, turn on the 15 volts power supply. Then press the power button on the synthesizer to turn on the unit. The next connection is the 18 volts DC power supply. The 18 volts rail is used for controlling the synthesizer. If separate power supplies are used for 15 volts and 18 volt rails, the ground terminals of both power supplies must be connected together before connecting them to the synthesizer. This ensures that both supplies share the same reference ground. If a dual-channel DC power supply is used, connect the common return terminal of the supply to the synthesizer's shared power ground. The 18 volts power supply must have a minimum current rating of 10 amps if the datasheet says so. After confirming the connections, turn on the 18 volts power supply. Slowly increase the output voltage until it reaches plus 18 volts. Next, connect the TTL supply. Connect the synthesizer wire labeled TTL to a 3.3 power supply. Connect the TTL ground to the ground terminal of that TTL supply. The TTL, lock, and the trigger signal share the same logic ground. When the synthesizer is successfully locked to the external 10 MHz reference, the lock indicator will illuminate. In applications where the synthesizer is installed inside an enclosure and the LED indicators are not visible, the lock signal can be used to verify that the external reference signal is present and the synthesizer has achieved a valid reference lock condition. The trigger signal is used when the synthesizer is configured to operate in external trigger mode. In trigger mode, an external pulse is provided through the trigger input to control the synthesizer's operation according to the required timing sequence. For applications that do not use trigger mode, the trigger wire does not need to be connected. The synthesizer can operate using an external frequency reference. Connect a stable 10 MHz external reference source to the ref in connector on the synthesizer. When the synthesizer successfully locks to the external frequency, the lock LED will illuminate, confirming a valid reference lock condition. If an external 10 MHz reference is not available, the internal reference can be selected through the synthesizer GUI. The detailed procedure for selecting the internal reference will be explained later in the video. The ref out connector provides the reference signal output. This port can be used for troubleshooting or verifying the presence and the power level of the reference signal. Finally, connect the computer to the synthesizer using the USB Type-C port. The computer connection allows communication with the synthesizer control software and GUI interface. Now, we will demonstrate the proper power down procedure before explaining GUI section. Always follow the bias down sequence provided on the synthesizer label and in the datasheet. Before disconnecting any cables or turning off the power supplies, first turn off the synthesizer using power button. Next, disconnect any equipment connected to the RF out port. In your setup, this port will have the antenna assembly, transition, and adapters connected. Using the GUI, disable the internal reference if it was enabled. Now slowly reduce the 18 volts power supply voltage down to 0 volts. After the 18 volts supply reaches 0, slowly reduce the 15 volts power supply voltage down to 0 volts. Once both outputs are at 0 volts, turn off the power supplies. Finally, disconnect all cables.